Welcome back to livecoding.ca. We are continuing to learn Rust today. Last week we finished up going through memory management in Rust, and today we are going to continue with the course from Microsoft on taking your first steps with Rust. Today we are talking about how to implement generic types and traits. We're going to understand what generic types and traits are and how to use them in Rust, what our generic types are, and how wrapper types use them. I'm not sure what a wrapper type is yet, but we'll get to there. Maybe that's like a type alias, I don't know. What traits are and how they help us define shared behavior, and how to implement an existing trait for a custom type, how to implement a custom trait for an existing type, how how trait bounds help us write generic functions, and how to implement an iterator trait to iterate through collections. We've gone through the Rust types already. We covered ownership and move semantics in previous streams. We'll go from there. Let's check out the intro for this module. A generic data type is a type that's defined in terms of other partially known types. We've been using many generic data types since the beginning of this course. For example, option of type T, there's the sum variant, and then there's the result with OK value of type T and error value of type E. And then there's the vector type, and there's also a hash map, which is the key value, so type K. We've seen the hash map with strings so far as the keys, but it can be anything, I imagine, and V for the value. And where we use generic types, we can specify the operation we want without many concerns about some of the inner types held by the defined type. Let's look at implementing a generic type here. We have the name of the type here. The struct here is called point, for example, and we're going to say point it has some properties here of type T. A point, it's probably number, but as you can see here, it can be whatever we decide. This one's Boolean, this one's integer, a float, this one's a string. That is where this generic part of it comes in. It's a point struct, but X and Y can be whatever this type T is. Like it says here, the point of type T struct can hold X and Y values of any type T, and it's a concrete type, the type T. If we try to create an instance of a point T that has values of different types as in the following snippet, our code won't compile. This makes sense because both X and Y have to have the type of type T, which is why unsigned 32-bit integer of 25 and a Boolean value of true will not compile. We're going to do cargo new. Cargo is what allows us to create new crates. Crates are like, think of them like NPM packages. And I'm going to call this one generics. And then I'm going to cd into the generics folder. And then I'm going to, the cargo new, what it generates is it generates a toml file, and it also creates a source/main.rs file. I'm just going to open that, and I'm going to paste in what we have here. We're going to go through it here to show that it will not compile. If I do cargo run, this will build the main.rs file if it builds successfully. Otherwise, it will simply output some errors. If we run this, I'm expecting an error. Let's make this a little bigger and see. Mismatch types. So expected integer found bool, not bull. It's not hard to say that, but it's kind of funny to say. As expected, 25 and true are not the same types, and it's a point of type T, where X and Y are of type T, which is why this doesn't compile. Again, this error isn't super verbose, but in general, I mean, it still gets the point across, but in general, a big thing I've been a fan of in the Rust language so far is the error messaging. It's really good. If we were to put this to like 30, for example, and I do cargo run, it ran, but it's giving warning. The only reason why it's giving a warning here is because those aren't being used. If I did print ln, for example, we use our formatter here, and then I say won't work dot x. And one thing I learned early on is semicolons are actually required in Rust. unlike JavaScript. If I run this, so we see 25 and 30, and we don't get any warnings now because we're actually using the values in here. Now, if we wanted a point of type t and u, and then we have x and y with different values, what we did would work. We can do this again, and there's some interesting things in here to touch on. Let's run this. It's gonna give warnings about things not being used, 7 warnings because we're not using any of these. But as you can see here, it's x is of type t and y is of type u. That's why we can have 5 and false, 1.0 and hey, and so on and so on. What's interesting is the last one. They're both true. They're both Boolean. There's nothing restricting us, like there's nothing restricting them, these two types being of the same type. These are the generic placeholders. Just wanted to point that out. If we come back here, so you can see here, like I was mentioning, the last one, it's bool and bool, or there's another one that's integer and integer. Even though we're saying pass in type t and type u, they're the same, and there's nothing wrong with that. That's kind of like a quick rundown of what generics are. One thing I've noticed that trips up folks with generics is, say you're creating some sort function and it's an array of type t and you're sorting. What would happen is, say I create an array of numbers. The array passed in is an array of numbers, but when you're in the generic function doesn't know that it's numbers. It only knows that I have an array. And that's important to note because an array has methods you can use. You can do like array.filter, map, etc. And you can use those regardless of what type the t is for that array, because this is available regardless of what that generic type is for that array. What you can't do is, like, say I pass in this array of numbers. If I get the first array item, I want to add 1 to it. That won't compile because when it's generic, it doesn't know that your t is a number per se. Because what happens if you did another generic where you passed in an array of letters? You wouldn't be able to say, like, add 1 to this array item, which happens to be a word now. That's why you have to remember about generics. It's like the most common thing about whatever the generic type is what you can use within that function or method. Let's talk about defining shared behavior with traits. A trait is a common interface that a group of types can implement. I wasn't really far off. It did sound like an interface when it was talking about it. The Rust standard library has many useful traits such as IO_read, IO_write, debug, clone, toString, default, and iterator. Each trait definition is a collection of methods defined for an unknown type, usually representing a capability or behavior that its implementers can do. Let's see here. To represent the concept of having a two-dimensional area, we can define the following trait. Area, where the trait is this function called area, and it takes itself and it returns a floating point 64-bit integer. Let's see how this would play out. We're declaring the trait by using the trait keyword and then the trait's name, which is area. Inside the braces, we declare the method signature. It describes the behavior of types that implement this trait, which in this case is the function signature. The compiler will then check that each type implementing this trait must provide its own custom behavior for the body of the method. Let's create some new types. Let's come back to VS Code here. 1 second. And I'm going to cd out of here, except I'm in the file and not my terminal. And I'm going to cargo new, we'll just call it traits, cd to there. Let's do code source main.rs again. And we'll close the other one. We're saying we have a struct circle. It has they're not properties. I believe they're called variants. It has this variant radius, which is a floating point 64-bit integer. A rectangle has a width and a height. with F64 as well for the type. And then we can say implementation of area for circle. I guess this is saying for the struct named circle, we're implementing a trait area, and then we have to implement the actual function itself because the trait itself is really more like the signature. If we look at here, so a circle, so we get, okay, the standard library has a constant for pi, and then we're getting the area for a circle. So that's pi times the radius to the power of 2. Is that what it is? Yeah. And then same thing for rectangle. We're implementing the area trait again, and we're saying we're multiplying the width times the height. That makes sense. And we're passing in self here, which I guess is because it's the instance of the circle struct when we're creating the circle and we give it a radius. It'll say like the current instance, let's grab its radius to the power of 2 and times it by pi. And same thing for the rectangle here. I think that makes sense. Let's check that. Now, if we keep moving along here, well, you know what? Let's grab all this here and let's come back to VS Code and paste this in here. It's going to complain that I don't have a main, so let's create the main again. And let's close the terminal for a sec. We're going to see here a circle, rectangle, and then we implement them. What we can do here is we can say let circle equal circle. I believe this is how you do the instantiate a struct. And then we'll say radius, and then we'll say 5. Okay, and then let's do print ln, and then let's do here. You know what? I'm going to take off that screencast mode. I feel like it's more of a nuisance than a help, but if you find it useful, let me know. And then we're going to say circle area. I have IntelliSense popping up here, and it immediately added area, but our circle struct gets this because this trait is being implemented. We all of a sudden have it available to our circle struct instance. If I run this, I'm expecting it to say output the radius, pi times the radius to the power of 2. If we do cargo run, ooh, interesting. Let's see here. I cannot find trait area in the scope. Oh, this is a valid error because I did not actually implement, sorry, I didn't add the trait. So I'm going to try and remember from memory here, trait area, and then we say area reference to self. So that's for the instance, and we're returning a F64. Is that right? Trait area. Well, maybe it's, no, what is it? Let me check. Oh, wait. This should be fn for function. I think that's okay. Let's run this. Let's see. Expected. It's again, I like how it's explicit. Let's do 5.0. Let's run that. And now I should get my, there we go. There's my circle radius. We can say circle radius, sorry, circle area for circle with a radius of has an area there. So then here I can do this, and say radius. Let's run this again. Cool. Circle with a radius 5 has an area of that. Okay, cool. And let's have some fun. Let's do the same thing with a rectangle. Let's say rectangle equals rectangle. If you're wondering where all that stuff popped in automatically, I'm using tab 9 in Visual Studio Code. It's pretty neat. We've got a width and a height, right? Let's say width. We'll say, I know these are trivial examples, but it's good to go through it anyways. And you're going to see here that should format things. Rust has a formatter with it. We're using a Rust format. I think it's called Rust-FMT, but it's nice. You know, if you're from JavaScript land or Ruby or even like C#, I know like it formats things. Or maybe that was an extension I had. Anyways, let's run this and we should see a rectangle as well now when we run this. Yeah, 20 by 30 gives us an area of 600. That makes sense. Yeah, so rectangle and circle. There we go. So we implemented a trait. Traits, from what I can see, are really interfaces if you're coming from an object-oriented language. I'm curious why they use the word trait. Maybe it should differentiate, but maybe there's more to it than that. Yeah, they went with showing the area, but I went a little further. Let's go to the next module. There's use the derived trait. What is a derived trait? Let's see here. You might have noticed that our custom types are a little difficult to use in practice. The simple point struct can't be compared to other point instances or displayed in the terminal. Because of this difficulty, you might want to use the derive attribute to allow new items to automatically be generated for the show. Let's take a peek at this. This isn't a generic right now. This is saying the 2 points are unsigned 32-bit integers, and then, or signed 32-bit integers, 2 points, and then we can't compare the values. That's because we need I guess a custom comparator, which was probably, we would probably create a compare trait, sorry. Let's see here. Can't print using the format specifier either. Interesting. Let's see here. Yeah, it doesn't implement format display, which is why we can't print it out. It says that it's not implemented for point. Yeah, it's saying in format strings, you might be able to use these other formatters for preprint instead. And what else is it saying? Point doesn't implement debug. If we try to print this out, it can't be formatted using the colon question mark formatter either, which I guess is the debug formatter. So let's keep looking down here. And then, yeah, it can't do a comparison here. So that doesn't compile. The partial equals, which I guess is another type of trait. That's a bunch of reasons why that is failing. We can use derived traits. Luckily, the debug and partial equality traits can be automatically implemented for us by the Rust compiler by using pound square brackets derive and the name of the trait. And it looks like you can have more than one trait in the parentheses there. Okay. The code will still fail to compile because Rust standard library doesn't provide automatic implementation for the display trait because it's meant for end users. But if we comment out that line, our code now produces this output. Okay, cool. Now let's pause there for a second. Let's go up here and I'm going to grab this code and let's go back to VS Code. Let's go down. Let's say cargo new derived traits. CD derived traits. Not cargo, code source main.rs. Let's paste this in. We're going to see all those errors like they were saying. Let's comment these out for now. And this still won't compile. It'll give the errors that they mentioned saying, yeah, it doesn't have the format displayer. Oh, whoops, I forgot to comment out one, sorry. If we run that again, it's still gonna error out. Yeah, exactly. It couldn't, the partial equals is not implemented. If we come back here now, let's go down and we can add this derive. Let's pull this. And these are traits that already exist, and I guess they know how to handle things regardless of us not implementing it. I guess the debug is able to take the self, which is the instance of point, and be able to print it out, I guess. And then the partial equals, I'm not sure how that's implemented, but I imagine it's going through properties and seeing if things are equal or not. But we'll see. If we run this, we get what we expect, which is not equal because 0.1 is x and y of 1 and 2, and then 0.2 is x is 4 and y is minus 3. For fun, let's make them equal, and it should say equal. That's expected. Let's put it back. So we can implement the display trait for our type. Let's do this. Let's come up to the top here. We need to import, or I guess it's not a namespace, but I guess the standard format module. And then I don't think the order matters here, but for readability, I'll put it after. We're saying we're implementing format : display for the point struct here. And then it takes, I guess the format itself takes self, which is the instance, the reference to the instance of point. And then I'm not sure about this here. F, it's a mutable format formatter. Okay. I wonder why we can't write print. Well, let's run this anyways, but I'm curious why we can't write print ln instead. But I guess that's, oh wait, no, never mind. It's because this is actually going to be printed out down in our code. We're saying write this, and I guess this is part of the standard formatter. It's okay. Let's run that now. Still get the same thing. And if we uncomment these now, let's take a peek here. You should have it print out points 1, and we can format it in 2 different ways. In the second way, it's printing it out like with debug information. The first one is showing how to print it out this way. That's interesting. If I remove this and ran it again, it would output the same thing twice. This is really for debugging. That works. That's great. Let's come back here. Traits, use trait bounds and generic functions. Let's check that out. Okay, I'm gonna take a sip of water for a second, and I'm also gonna move Todd up a bit to see if he can win the race. It's kind of neck and neck there. I'll throw out those help commands again. Yeah, let's give Todd one more up. You can do it, Todd. You can do it. If we come back here now, use trait bounds and generic functions. Like we were saying, so traits are interfaces that you need to implement on some kind of data type in Rust if you want to extend it. Like we saw, we had the area trait, and we implemented an area function, which I guess becomes like a method on the instance of the struct we had there, like a circle or a rectangle. Traits let us define functions that accept many different types, because when a type implements a trait, it can be treated abstractly as that trait. Let's see here. We can declare function arguments to be an anonymous type parameter. That was hard to say, anonymous for some reason, where the callee must provide a type that has the bounds declared by the anonymous type parameter. Let's see here. We got a web app, and we want to convert something to JSON. We would say as JSON, for example, and we implement this function as underscore JSON. It takes the instance, which is the ampersand self here, and it returns a string because JSON is string. Let's see what we got here. So, interesting. We can say send data as JSON, and we get a value, and that value is of type some data type that implements the as JSON trait. Yeah, so that means this is generic in the sense that I could have a circle that calculates an array. I could have an area. I could, I don't know, let's see what else. Could have, let's see here, a car with all its pieces, but both of them can implement as JSON, because at the end of the day, as JSON returns string, regardless of what these different data types are, as long as they implement as JSON, the as JSON trait, we can actually use send data as JSON, this function here, which I think is kind of cool. And this is kind of like you're narrowing the what the type is, which is kind of nice, because then you don't end up with something like send data as JSON where the value is a car, where it's this other thing. And I imagine you could probably say where it's of type T, but it has to implement as JSON. But I'm guessing in Rust, this is probably the way you do that. But let's read on to see. Yes, we don't give a concrete type for the value parameter, and we specify implements a keyword. Sorry, we specify the impl keyword and the trait name to say that it implements this trait. Now we can see here. Yeah, so, okay, yeah, this is another way to do it, I guess. Yeah, this is kind of what I was saying, where type of T, and it is a type that implements as JSON, and then here it's the reference. I think the difference here, though, is if you pass in the T, you have access to the whole T. But again, because this is a generic function, if I pass in a car, which implements as JSON, or a rectangle, which calculates array, and that it implements as JSON to return the width and height, I'm not going to be able to know when I'm in this generic function if it's a car or not. I can't access anything that's car related or rectangle related. I can only access what's common to the generic type, which is in this case the JSON. Let's see here. We have a struct of person, of dog, and then we implement as JSON for the dog and the person. And then we create instances for each of these, and then we say return it as JSON. I'm gonna go ahead and copy this. I can obviously type all this out, but I kind of get the gist of what's going on here already. Let's come back in here. Whoops. And nope, that's not what I want to do. Keep this here. So reiterate, so we have a struct of person, we have a struct of dog, and then the person implements the as JSON, which is returning a JSON string based on all the properties that a person has. Same thing goes for the dog. And then in here, if we go function main, let's pop this here, and I'm having trouble typing. Let's say let person equals person, and then what properties do I have here? Name, and then we'll say string from, and let's call them, let's see here, we'll call them the weekend, and then we'll add age. I have no idea how old the weekend is, but let's say 28. And then what else do we have left in here? Favorite fruit. I am gonna guess that the weekend loves, let's see, maybe the weekend is like me and he's a big fan of melons. I've been eating a lot of honeydew lately, so let's go honeydew, string, don't need that extra one. Okay, let's save that. Should always put the semicolon, and then boom, we've got our formatting. Okay, and then let's do send data. Oh, I don't think we've implemented that yet, have we? Send data is JSON. Did we not implement? No, we haven't implemented it yet. That's fine. Let's put it up here. Let's close up. Main's closed already. Let's come up here, and then we'll say function send data JSON. Then we'll say value ampersand impl as JSON, and then we'll say string, and then we'll say, all right, you know what? I'm not gonna return string. I want to print it out right in here. This is, send the data as JSON. I'm assuming we'd be sending it to like a web server or something, but for learning's sake, I'm going to print it out in here since it's a string. I think even with strings, you need to pass in a formatter, but we can check that after. So this is saying value at impl JSON, and then we'll say here, send data as JSON, and we'll pass in the person instance. And I believe that should work. I always like to try it before going through, but I cannot find trait as JSON in this scope. Oh, I forgot to define the trait, I think. Yes, that's right. We would say trait as JSON, and then its function as JSON self string. Sure. Is that right? Let's try that. Okay, let's see. We got cannot be formatted with the default formatter. Okay, let's see what as JSON is defined as. Okay, value impl as JSON. That should be. Oh, I gotta pass a reference, I believe. That's my bad. Is that all it is? Maybe. Let's see here. Let's do $person. Not still some errors, but let's see what it's saying. Impl as JSON with the default formatter. Okay, I'm gonna try formatting it with, where is it? Where did you go? As JSON, not there, here. Let's try the debug one maybe. I'll go look at the code in a second here to see. Still got an error. So cannot be formatted using, because it doesn't implement derive. Let's do that. Is it this? Derive, debug. Is it derive like that? Let's try that again. It can only be applied to structs. Sure. There we go. Person. Let's put that on there. Maybe that'll run it now. Still got some errors. I'll go take a peek at what's going on here. As JSON doesn't implement debug. Let's remove this and let's see what they're saying. I kind of like to always go off script a bit to mess around with things. We've got some errors, so let's see what's going on here. Let's come back up. So note that both person and dog implement the as JSON trait. We can use them as input parameters for send data as JSON. That makes sense. Let's see what else here. But what happens is when we pass a type that doesn't implement the expected trait to the function. Yeah, that's so this is like at compile time. Cat here, the cat struct doesn't implement as JSON. It's complaining that it can't compile here because of that. This error happened because we tried to use a type that doesn't implement as JSON. That again. Optional challenge, you can try to implement the as JSON for the cat type. That's so good. I want to see something in the playground, like maybe I missed something. Let me zoom this in here a bit. Bring this down. Send data is JSON. Print as J. Oh, okay. Maybe I can't do the print ln right away. Let's bring this in. Come down here. Let's replace this with this. So print sending JSON to the server. We're getting the value, and then we're saying done. Sure. Let's clear down here. And I think this will run now. Yeah. I was doing something incorrect in my send data JSON. And oh, you know what I did wrong? If we undo this, I I didn't do as JSON. That was why. If I do this, it's all good probably. Yeah, that's fine. And in fact, we don't even need that, I don't think. Yeah, so we can output it like that. And there's our piece of JSON. Let's move on here. Let's close the playground. And we're going to take a look at iterators now. We've already covered how we can iterate over a collection with using a loop. But now we're going to see how Rust covers the concept of iteration itself. All iterators implement a trait named iterator that's defined in the standard library. And it's used to implement iterators over collections such as ranges, arrays, vectors, and hash maps. This looks like an iterator, like even in, think when you yield in JavaScript, you have your next, it's not exactly like this, but you have your, this is like the current item, and then you go get your next one. And I believe, does it options help? Yeah, this returns the item. I think in JavaScript, it was more along the lines of if you've hit the last one, it says done is false, I believe. Anyways, no biggie. Let's look at this here now. We've got type of item, and we have self : item, which defines an associated type with this trait. And if we remember also, this is the option enum. The option enum will give you either the type of self : item, or if there's nothing there, it returns none. Okay, and we saw that when we were working with some pattern matching back in It's either first or second stream. Those are available if you go to youtube.imdeveloper.com. I have the past ones there, so you can check that out. Now we're going to look at implementing our own iterator. It takes two steps. We need to create a struct to hold the iterator's state, and we need to implement the iterator for that struct. Let's take a peek here. We have a counter struct, which has a length and a count. And then in here, we implement a function called new, which takes a a length of type uSize, and it returns a counter, and the counter starts at 0 and it has a length of whatever we pass in. Let's see here. Let's copy this over here. What should I call this? Yeah, I'll call it implement our own iterator. Cargo new, we'll say implement iterator. Cd implement, code, open up the file. Cool. And we've got our counter. We're using the debug trait. We're deriving it, so if we need to print it out. And let's go take a peek what else we've got to look at in here. We implement the iterator for counter, and we have an item, and then we say get the next one. So it's mutable because we do need to increment the count. That's why we have the mutable reference there, not immutable, to be clear, mutable. What we're saying is when we get the next one, we want to increment the count by 1. If the count is less than or equal to the length of the counter, we want to return the count. Otherwise, we return none because it's an option of type uSize, I believe. Let's take a peek at that. Let's copy this. This is what we need to implement. And then if we come down here, implement iterator for counter. Function new. I guess this is kind of like a constructor. The counter struct needs to. Okay, yeah, that makes sense. I guess this looks like a trait. Well, I guess it is a trait. I guess maybe this is called a constructor trait, maybe when the struct and the impl counter has. I'm wondering. I'm curious. Like, why not do why is this not highlighting? Why not do this instead? Expected field declaration. Yeah, I guess like you could say new colon and then some function, but let's keep with what we got here right now. But this looks like how you create a constructor for a struct, because I guess in this case, well, let's see, we'll take a peek here. Like we were saying, this is the implements the iterator. So that's the next there. And if we come back here for 1 second, we're going to say create a new counter, which is where we saw that impl counter. We come back here. What I'm curious about is this should run. There's some warnings, but that's fine because we're not using everything. But what I want to see is, what if I say counter and I do this, like counter, and then I say count is 20, and let's say length 40. Like looking at this would mean that our counter starts at 20 and it would stop once the count hit 40. I want to see if this compiles. My feeling is because we said up here, impl counter, meaning we need this is the constructor, I don't think it's going to allow us to do what I did, which is say, create a counter like that, but could be wrong. 3 warnings emitted. Let's remove this dot mute, sure. And then let's run this again. Interesting, there's nothing stopping me from doing this, but we might revisit that after. Let's go back to what we were saying here, which is counter new 6. The counter is, if we look at the code here again, the length is 6 because that's what we're passing in here to the new. And the counter will go from 0 to 6 and stop. All right, and let's run this. Yeah, there's still the 2 warnings, that's fine, but okay. Now let's see in terms of the iterator. Yeah, we're doing the next and stuff. So it's gonna copy what we got here. And so let's close this for a sec. We'll read through this quick. Like I said, we're gonna create a counter of length that has a length of 6. As we created a counter, this is to debug it to show what it looks like. It'll probably say counter 0 for count and 6 for length. And then we're saying get the next one. That's going to return us the count, which should be 1. And then 2, 3, 4, 5, 6. And then every other one after that, because if we look up here, the count is greater than self.length at that point. So it's going to return none all the time now. So we can run that. Let's clear this. And I'll bring this up a bit. And we should see. So this was the debug and counter exhausted, because at this point the count is not, it looks like the count is still going up, but because it's gone past the length, it's just always returning none. But counter exhausted, yeah, that makes sense. Further calls to next will return none. I'm looking at one other thing here. We could probably make this even a little more efficient, maybe, if we add it there instead. Now, if we run it, it should say exhausted counter length 6, 6, I believe. Created counter. Oh, panicked. Left some 7. Yeah. It's failing for good reason. Counter dot next left is some 7, but we expected none. Why did it do that? It's clearly because I changed the code, but if it's less than or equal to, let's see what's going on here. Let's see, if 0 is less than 6, let's increment the count. And then if we get here, 6 is less than or equal to self.length, we add 1 here. Yeah, it adds the extra 1 there. And then it's saying that things aren't right, I guess, but I would have expected that to, let's run this again. See, it's still doing the count. I wonder why, still not sure why. It's something silly, but I won't dwell on it too much. But what we're seeing here is that it's gone next. We do 1 all the way to 6, and you keep getting some of something. And then at that point, it keeps saying that I'm returning none, and I'm returning none. And you could go on forever at this point, and it will always return none. Calling next this way gets repetitive. That is true, especially if we don't know how long you would literally have to do it. You would literally have to like paste that assert equals, for example, n number of times whatever the length is. Rust allows us to use for loops. Oh, excuse me, small yawn there. Now we're going to do a for loop, and because we implement the iterator, it knows to grab the next one. So we can simplify it to this. We come back here. Let's call this main old. Come here. Oops. This is should output 0 to 10, I believe. Oh, sorry, 1 to 10, because it increments. But this is nice. We've implemented the iterator up here, and we went through this example here where we explicitly do next, and you could still do that, but because Rust knows it's an iterator, we can loop through it and it'll get the next item. And we don't even have to worry about it when it says dot none, because I imagine once we get to dot none, not dot none, but once we hit the point in the iterator where it says option of type T is now returning me none, then it knows that the iterator is done. We don't need to do this these are explicit assertions here, but we would never even run into it hitting none at this point. The loop would finish. Let's give Todd a little boost up there in the race. I think That makes a lot of sense. The iterator traits full definition includes other methods too, but they are default methods. They're built on top of Next. You get them for free. Let's see here. So we could do sum. And so what this would do is it would do 1 plus 2 plus 3, etc., all the way to plus 10. And that's what the dot sum would do, I guess. And then the other one is let powers of 2. We're saying a new counter. We can map over it. We get the current number. We're saying 2 to the power of n, and then dot collect. I guess dot collect is what, when you map, I guess, that's what it returns. Like that's how you're able to say return the value you calculated, maybe. Maybe this is something related to the math.pow. Here we're saying powers of 2, the vector of these numbers, I want to map over them, and it will assert that each one that it got mapped to, for example, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, etc., etc. I think that all makes sense. And let's take a peek at those. Let's add them in here for fun. And we can say that. And those two should assert. And for example, if I said 54, should error out. Expected 55, got 54. And I'm curious, in the case of asserting a vector, will it show the whole vector and show which one was incorrect? It does. It debugs out the whole vector, I guess. That's kind of neat too. I think the sum is pretty neat to have out of the box for an iterator. I'm curious about the dot collect though, because this is saying map over each item in the vector, and we don't need to do an explicit return. Oh, I see. And then map, and then this is outside of the map, so dot collect. I wonder why you need to do the collect. This will give an error, I'm sure. I want to see why. Expected struct vec found struct map. Oh, okay. I guess collect converts a struct map back to a vector, perhaps. If we did that, well, yeah, I think that's what it is. Let's move on to the next thing here. Let's implement a generic type. In this exercise, you'll transform a container struct that only accepts positive integers of the U32 type into a generic container that can hold values of any given type. Don't edit any content inside the main function. This exercise is complete when the code compiles. Okay, let's grab this, implement a generic type, sure. Let's do cd cargo new, implement generic type, cd implement generic type, code, blah, blah, blah. Let's open up the main.rs. Let's paste this in. So we're saying we want to assert that 42 is equal to 42. If I run this, this is not going to compile, except I did not compile it. I opened the file again. Let's do this again. If I do cargo run, it's going to give me errors because it's always expecting a U of 32. The foo here is not going to be equal to foo here. Let's come up here. Container is of type T, and then we'll say the type is T. That's all good. Now we're going to say implement container. This is pub, I guess, for public function, and it's a constructor. And we'll say T, and I would guess we have to do it like this again. Now let's try running this. Interesting. Let's see. Implement container T, not found in this scope. Maybe for implementing, I don't need to, because in this case, again, this looks like the trait to allow you to add a new, like a constructor. I wonder, new value T. Let's see if that works. No. struct container t, struct defined here with one type parameter t. Yeah, use angle bracket set missing type argument. Yes, I had that. Now, why didn't it like the previous thing though? This will give that error again. So maybe you don't need to do this. No, but you do need a type. Okay. I would assume that I can use the t there. T not found in the scope. Cannot find type t in the scope. Let's try this. I don't think I should have to change the letter here because it's a separate thing, but let's try this for fun. Not still complaining. Cannot find type u in this scope. Cannot find type u in the scope. Sorry, I got an itchy ankle here. I mean, this is definitely okay. That's how I would do it in C# or TypeScript. I'm curious why I can't do it here. Maybe it's like this, because let's see. Nope. Struct container t. Yeah, it's expecting the type up here. Like I definitely need the type up there. I'm gonna leave it as u for now to distinguish it from here, but yeah, I've added the missing type arguments. I will look at the solution at some point, but I'm surprised this isn't working. Oh, maybe. No. Cannot find type P on the scope. Well, maybe it has to be, oh, maybe it has to be T because of the T up here, but be surprised if that was the case. Not found in this scope. Let's get rid of all of this and then see. I don't see this working because you need to know like the generic being passed in. Like it has to be on there, but let's run this. Yeah, struct container t with one type parameter. Use, yeah, see, it's telling me to add the t here. I get that. And then that should be fine, but then let's try again. Same error. Could not compile implement generic type. You know what? Let's run the Rust C command and see. Impl something error type name. Oh wait. The type name is not in scope. And error n is not in scope. fn foo xt, which is what I was doing. Type name t is not in scope. Please verify you don't misspell the type name. Struct something, sure. Maybe I have to do this. Container t, maybe I have to do this. Type t, fm bar value t. I find it odd that I would have to do that, but sure. But they did show that in the previous example, so no, 4 errors now. It's getting worse. Inherit associated types are unstable. No, then it can't be that. Okay. I'm pretty comfortable with generics. I'm kind of perplexed why this isn't working. So clearly it's implemented differently, or I'm missing something super obvious in the context of Rust. Let's look at the solution. Implement container t. Okay, I have to pass in another t there. Oh, okay. I'm guessing here, but this is the container of type t where we return a value of type t. We're implementing the container trait, which is gives us the new, like the constructor, and it is of type t, but I guess we need to say that this type t is coming from the implementation here, which is of type t. I think that's the only thing I'm missing. That did not seem obvious. If we run this, I would guess it's good now. Yeah, interesting. If we do u, and because these are placeholders, this shouldn't change anything now. Yeah, it's all good. Interesting that you have to pass it in here. Now, yeah, I do find that odd, but guess it makes sense. For fun, I'm gonna try something. We did tu here, and then we would say count u, and then this should give an error now, but I can't set the I can't set the count in here as well, so, but let's see here. Count U T, if I do count U, let's see, I'm gonna, yeah, this isn't gonna work. U T U T, it should be TU actually. This will work, but it's not what I was trying to demonstrate here. I was trying to show that it's really whatever you're setting here, it looks like you have to set it here, and then you have to set it again here. Because if I run this, it's probably going to complain about count. Expected, oh yeah, expected 2 arguments. If I do, okay, I'm not going to do all of these, but if we did this, for example, let's say hello, new string, yeah, this will still compare the value here. String from, why did I have double here? Assert new 1 2. Okay, new, yeah, that's right. Okay, so this should compile now. Of course, let's give it an error now. Oh yeah, I'm not setting the count. It all runs there now. I was trying to demonstrate that you do need to pass in both because there's no other way. I don't know, this example of showing what I was trying to convey is not good because it just, I think the general rule here is if you're implementing some kind of trait, and maybe this is only for when it's the actual container type, sorry, whenever it's the impl is contain, not container, but the same name as the struct that you have to do this. I'm not sure, but I'm gonna undo this, come back here, get rid of count. We're back to where we were. That should be all good. Yeah. So TLDR there because I went on a tangent, but it looks like you need to pass in the generic type here as well, which I find kind of odd, but I guess that's how it goes. I'm gonna revisit that, I think, after the stream and see. All right, so now we're gonna implement an iterator that returns equal items in a sequence grouped in vectors such as 1 1, 2 1, 3 3, and then so it does outputs that, then that, then that, and 3. I guess if it's the same value, keep grouping them, and then when it value switches, then you start a new grouping, and so on. Okay, the generic type T will need to be an implementer of the partial equals since you'll need to compare values to perform the assignment. Okay, we don't need to worry about that though because that part's already solved. Great. Here's the whole thing. Let's look at this. So, okay, let's implement iterator again. So it's clear. And then let's go cargo new, implement iterator 2. Sure. CD implement, do code. Let's close that. Paste this in, and let's take a peek at what we got. We've got a vector, we've got groups. Groups are of type T, and then we have this inner variant, which is a vector of type T. And then again, we see this, we have to pass in the generic type here as well. Here we're saying if we want to create a new group, it's of type T, where the vector is of type T, which maps to the inner up here. And we're saying groups inner. I think that implementation of that makes sense. Implementation T partial equals iterator for groups of T type item vector T. Write the rest of this implementation. Groups, new data, which is a vector here. If we look at this, this should output this. It should look like this. 4, 1, 1, and it should be 2. Writing it out explicitly, but it's good to visualize. Then this would be minus 2, minus 2, minus 2. Then we would do 5, 5. That's what I'm expecting to get. Okay. And then, all right, so iterator for groups. item is vector t. All right, next, let's see here. We'll finish up with this today because, oh, it's already 1:30. I'll finish this up and then we're going to call it a day. I want it to look like this. So I'm going to bring this up here. And then iterator for groups of T, group new, inner groups, groups new vector, data vector 2, assert equals this and this. So we're saying new data into iter dot collect. Okay, I guess we say function into iter, and then we're getting, let's see here, don't have to do the for here. Let's see here, what's going on? Into iter, because that's what this is here. Partial equal into iter. Maybe it's not this. I don't know. My brain is getting a little sizzled here. Into iter. Is into iter. I don't remember seeing that as part of the implementation of the iterator. We come back here. I'm gonna look into iter Rust. What is this? V into converts it to an iterator. Then new data, iterator, and then collect. This is just, I don't know, I don't need to do into iter. I need to go back to creating the iterator. And how are we doing that again? Let me look at iterators here. Oops. Yeah, let's close that. Iterator 4. Yeah, switch the next. And then we have the item there. Let's do this. Self item. Let's save this. Now we get a vector. Vector 4. Interesting. We're iterating over the current vector. Let's see here. We need to create a group, new inner vector. Where can I add to that though? Because we basically, I'll write the pseudocode out. Let's see here. If item is same as previous, add to vector. Otherwise, create new vector. That's what we want to do. Okay, and let's see here. Item is type vector t, and we're going over self here. I'm going to implement the iterator here on the next stream because my brain's a little cooked. I think we're going to stop here for today, but wanted to say thanks for everybody who came by. We will see you next week.